Today, we'll be learning how to find the powers and roots of complex numbers using a special theorem. We all know that the rectangular form of a complex number is z equals to a plus bi.
But besides using the Cartesian or rectangular form, there are many ways as to how we can express a complex number, such as using the polar form or Euler's form, all of which can be expressed using an Argand diagram that is very similar to the Cartesian plane we use within x-axis and y-axis. In the case where we have the complex number z equals 1 plus I in Cartesian form, the value of the real part A will be 1 and the value of the imaginary part B will be 1 as well. Now let's try to plot z on an Argand diagram. Like a Cartesian plane, an Argand diagram consists of two axes, which are the imaginary and real axes. Earlier on, we learned that the imaginary and real parts of z both equate to 1. So just like how we plot a point with coordinates 1, 1 on Cartesian plane, we can plot z here as well. This will create a triangle on the Argand diagram that will help us translate z into other forms. Now, how can we approach this question? One way to tackle this problem would be to expand this binomial 1 plus I using the binomial theorem. Now let's try to expand this. For the first term, we have 5 choose 0 times 1 to the power of 5 times I to the power of 0, and we can work out the other terms using the general formula above. Eventually, we will arrive at this expression here that boils down to the complex number negative 4 minus 4i.
Although binomial expansion is an option, this is not the most efficient way to solve the problem, and thus we will have to find another method. First, we should try to convert this into polar form, where z equals to r cis theta, r being the modulus. We can draw this out on an Argand diagram and find the angle in the modulus. Let's sketch it out on an Argand diagram where the y-axis represents the imaginary number and the x-axis represents the real number. Thus, we will get a triangle of 1, 1, and root 2, which means our modulus r is root 2. In order to find the angle, we must remember that this is a special triangle, therefore the angle theta will be equals to 45 or pi over 4. Therefore, we have found the polar form of this number. Now that we have found the polar form of the number z, we can use de Moivre's theorem to solve for z to the power of 5. De Moivre's theorem allows us to find a complex number raised to the power of a certain number. Using de Moivre's theorem, we only need to raise the modulus to the power of 5 as well as multiply theta by 5. Thus, we will obtain the new answer. We can also expand this out, which will give us 4 root 2 cis 5 pi over 4, and thus, by expanding, we are able to obtain the final answer in rectangular form, which is negative 4 minus 4i. But hold on, how did we even derive de Moivre's theorem in the first place? Now let's imagine that we have two distinct complex numbers. The first is z1 cosine alpha plus I sine alpha, and the second is r2 cosine beta plus I sine beta. If we were to multiply these two complex numbers together, we would first have to multiply the modulus, giving us r1, r2, and everything that comes after that, which is cosine alpha plus I sine alpha times cosine beta plus I sine beta. With this, we can expand the contents in the bracket and obtain a simplified answer, using the trig identities known as the double angle formulas of sine and cosine. Now imagine if both of these complex numbers were equal. If you try and use the same logic, you would appear to find a pattern, which essentially is de Moivre's theorem.
Before we end this video, let's try to do this question here, where we have to find the square root of 7 minus 24i. What are the strategies we can use to solve this? Do we use de Moivre's theorem or binomial expansion? Now, let's try to tackle this problem using de Moivre's theorem. First, let's try to locate 7 minus 24i on the Argand diagram. Using the Pythagorean theorem, we can easily find out that the complex number has a modulus of 25 and an argument of approximately negative 0.284 radians or negative 16.3 degrees. However, it does not create an ideal type of special right triangle that would enable us to express the argument as an exact value, which will make it rather challenging for us to manipulate the entire number later on and to process the square root in the question. Hence, in this case, doing binomial expansion may be the better way to go. Let's try this out. First of all, let's start by letting a complex number z be a plus bi and assume it is equal to the square root of 7 minus 24i. We can then square both sides and expand the product using binomial expansion. On the left-hand side, we have a squared plus 2abi minus b squared, which is an expression obtained from a plus bi squared. And we have 7 minus 24i on the right-hand side. Then we can equate the real and imaginary parts and form simultaneous equations, which we can use to solve for a and b respectively, using the method of substitution. Eventually, we will be able to arrive at the equation a to the power of 4 minus 7a squared minus 144 equals 0. We can factorize this equation to two quadratics below, where we can reject a squared plus 9 equals 0, as it will give us imaginary a values. Now, by solving a squared equals 16, we can easily see that a can be either positive or negative 4. Using these values of a, we can quickly find the values of b using the simultaneous equations and arrive at the two complex numbers, 4 minus 3i and negative 4 plus 3i, which are the solutions to our problem. We hope you enjoyed our video. Thanks for watching!